This video is to show you the valence band measurements, the cutoff measurements, and the Fermi edge measurements using KherveFitting. So you can go into the file and go into Open Examples, and you have a list of folders, and in there we have valence band. So let's use the AU valence file. So in here we have 3 files, and one is set at different um, number because I've shifted the data by 29.5 because I applied a bias voltage, and that is why I've put it there. So now this is already fitted, but I'm going to start with the Fermi edge. So the Fermi edge data or results will look like this. And if I open the valence band minimum, it will look like that. Okay, so what is it? So we have two sets of measurements, the Fermi edge measurements, and then the valence band stroke cutoff measurements. And let's remove the data that we got. So to measure Fermi edge is very simple. It's using the LM-Fit XPS by Julian, and we can simply add the range and fit the Fermi edge. And this is now fitted with a nice extrapolation, and we get a center position of 0.181, and it gives me, using the LM-Fit XPS library, it gives me some thermal broadening and maybe some strange instrument resolution. I left it for now, but the most important for me is the resolution of our instrument. So for some of the system company like Omicron or Thermo, then we'll tend to look at the 16 to 84%, and this would be the it will provide the 396 milliev. You see it quite differ. If it's 10 to 90, it's straight 538, and 20 to 80 is 339. Obviously here we have the thermal broadening, so that's why we have an extra 122 milliev that was added to it. Okay, so that's how that's the type of data we want. Now let's look into the valence band measurements. So let me remove the valence band measurements. And so this, sometimes the vertical lines is gone, just like here. So let's remove the Fermi. It may do that too. You can see it's not coming back. So just close it and open it, and you'll get the Fermi, you get the vertical line. So you do need the vertical lines. You can see minus 0.22 here, and that is in the center of the edge. And then 13.38, that seems to be the one for the background center. So this is the valence band minimum, or the edge used here. So we'll use that here. So for now, we'll consider the background to be 0. And so the valence band minimum will be the intersection of this line of with 0. So now we will say we have it here. So we're going to create a line, and we are going to fit 10 points to that. So let's just do the calculate VBM. And there we are. We can see in blue our 10 points. Let's shift the data just like so. And you can see how well that fits. You may decide to put it somewhere else, and now you get it at 0. So let's say actually I wanted it somewhere here. You just redo, and now actually it's the same thing. So let's just continue one more time, and maybe put it somewhere there, and you can see now it's changed quietly. So it's up to you to do what you want, but I would consider to actually use the background. So here we have the background that needs to be extrapolated. So let's just first put our thing here, and then our line, and then the center of our background will expect to be here. We have to tick this box, and then we may add more points, maybe 20 points. And then if we calculate the VBM. Now our 0 is no more the same. We have an extrapolation. We can even increase this, see quite nicely how this has been extrapolating. It looks quite good. So now, as a result, this is shown as VBM 1.82, and this is all we need. We can obviously think and do exactly the same thing using the cutoff. So let's go back to cutoff. And now here we have a valence band, sorry, we have a cutoff which was measured on the thermo-K alpha, and this was on the gold. And then I spotted the gold to the best I could. And then I've offset all this because this was done at 29.5. That's why I've applied 29.5. And now I can simply use again, the vertical lines are gone. So I'll just go back. I'll use the VBM. You can see they are back. And I can just see where this is moving. So this is the center of the edge. So that's what I want. I will put it there, and this would be my data, so I'll put it anywhere. Obviously, I was trying to show the possibility, so that's 10 points. Calculate the cutoff, as you can see. This is done just at 0 because I forgot to click on there. So now this is the valence band, sorry, the background, and then my cutoff line. And if you calculate the cutoff, now you get this line, and this is not correct. That's what I wanted to simply show, but I can obviously doing it better. So this is the center line, and maybe somewhere there I can decide to use 40 points, calculate the cutoff, and now this is more what I would expect. As you can see, the line is very nicely extrapolated with many points, and the same for the cutoff line. So the results is shown here, 1481.32. So obviously we have to remove the 1486.67, and that seems to give maybe around 5.2 EV. Okay, that will show. Yes, maybe one last thing, sorry. Those are represented. So this is how KherveFitting knows this is a cutoff. So if I go from one to the next, it still stays there, and the results is all shown because we have as a fitting model, and the fitting model is not shown here, but we have as a fitting model, if you go into the show all range, let me go again and remove this, show all range, we can see here is VBM. That's why he knows that there are 10 points and so on and so on. Then the result is still shown here, 1.82. This is what we want. And if we go to cutoff now, this is called cutoff, and the fitting model is cutoff. And then the result is 181.32. And it also gives me the range at which the center points was taken and where the background was taken. So this is all written. And the same is now for Fermi edge. So the Fermi edge is called Fermi, and then it gives me again where the range was taken, and that's it. Okay.